This is our first lecture video for Chapter 13 on chemical kinetics. So you may be wondering why there's a picture of a lizard on this slide. Lizards are cold-blooded animals, they're reptiles, and their body temperature is dependent upon what the surrounding temperature is. And the author actually starts out with this chapter of the book telling how his kids actually catches lizards, because lizards are very fast. But if you were to throw cold water on the lizard, their body temperature drops rapidly. And when their body temperature drops that rapidly, biological processes and chemical reactions that help them move can occur. So they actually slow down, and sometimes they'll even be stunned. And once they warm up, then they're able to run and move around very quickly again. But the kids actually catch them by throwing them on the cold water. This stuns them and temporarily freezes them as in freezes their motion. But they grab them up and then carry them wherever they want to and warm them up, and the lizards run around again. But what does this have to do with chemistry? Well, it's those chemical processes in the body that allow the lizard to move that are affected by temperature. And when it gets colder, the reaction slows down. And that's what chemical kinetics is about. It's about studying the rates of a reaction and how fast they go. So kinetics is the study of the factors that affect the speed of a reaction and the mechanism by which it proceeds. And the mechanism is just the route at which the reaction takes, the pathway it takes. Now, experimentally, it's shown that there are 4 factors that influence the speed of a reaction. First is the nature of the reactants. 2 is temperature. The third are catalysts. And the fourth is concentration. And we'll actually discuss some of these in more detail later on. So let's look at defining rate. And we'll take an example of you driving your car. The speed you drive your car is a rate. There's a distance your car travels in miles in a given period of time. So the rate of your car has units of miles per hour. So your speed is the change in distance over the change in time. Thus, rate is how much a quantity changes in a given period of time. So we say something's faster because it covers a longer distance in a shorter period of time. Now let's define the reaction rate. The rate of a chemical reaction is generally measured in terms of how much the concentration of a reactant decreases in a given time period. But we can also look at how the product concentration increases. Now, for reactants, a negative sign is placed in front of the definition. So we said that rate is the change in concentration over the change in time. And the rate, when we're looking at in terms of product, is the change in product over the change in time. And remember, change is always final minus initial. But because in a reaction, the reactant is being consumed and being made into product, so we're losing some of the reactant, the change of the reactant will be negative. So to get rid of the negative sign, we multiply it by another negative sign. This way, when we look at the rate of the reaction, no matter how it's determined from the product or the reactant, we get the same value. Now, reaction rates are going to change over time. As time goes on, the rate of a reaction generally slows down. So this is because the concentration of the reactants decrease. So initially the reaction starts off very fast, but over time, because you're losing some of those reactants that you started with, the concentration is going down, the reaction is going to slow down. So because you've got fewer reactants, you've got less probability of the reaction actually occurring, and the right proper orientation and the probability of those molecules coming together to cause the reaction. Now, at some time the reaction stops, either because you've run out of your reactants, you've run out of your starting materials, or because the system has reached equilibrium. And remember, we defined equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. Here we're going to look at 2 reactions. We're going to represent this one on the left as a fast reaction, so we've got the little bunny running, and on the right we've got a slow reaction, so we've got the little tortoise running. And at time 0, we've got only starting material. We've only got reactants. So we're representing our reactants as the blue cylinders and the red spheres going to make the purple ellipsoids in this fast reaction. But in the slow reaction, we've got the cylinders and the blue spheres reacting together to make the green ellipsoids. Now after 16 seconds, the fast reaction's halfway done. You've got half products and half reactants. But in the slow reaction, we've only formed one product, so we're mostly reactants. So it's definitely going slower than the faster reaction because we have fewer products being made. Now after 32 seconds, we've got mostly products for the fast reaction. Notice we've got 1, 2, 3, 4, 5, 6 of the ellipsoids, and we've only got 2 of the red spheres left. But in the slow reaction, we've only made 2 products now. And after another 16 seconds, the fast reaction's finished. It's all products. But the slow reaction's not finished. There's only 3 products formed. It's not even halfway done. So let's look at the data associated with the slow reaction a little bit more closely. We're looking at time 0 and time 16. So here we're looking at the change in the concentration of X with respect to time. So initially we had 8 of the reactants X, so the yellow cylinders, and at time 16 we now have 7. We lost 1. So the change in X, the change in concentration of X, is final minus initial, so that's 7 minus 8. And the change in time, we went from time 0 seconds to time 16. So 16 minus 0 is our change in time. Now because we are losing reactants, remember we're going to get a negative sign here, we want to get rid of that negative sign. So when we're losing reactants, the rate of the reaction, we have to put that negative out in front. So the rate of this reaction is 0.0625. Now let's look at this reaction rate in terms of producing product Z. So the change in concentration of Z over time, at time 16 we have 1 product, at time 0 we have 0. So 1 minus 0 over 16 minus 0, and the rate is 0.0625. So no matter which reactant that we're looking at, the rate of the reaction is going to have the same numerical value. Now let's look at going from time 32 and looking at the change in concentration of Z. So we're looking at going from time 16 to time 32. Well, the final Z concentration in time 32 is 2, and at 16 we said it was 1. So the rate from there is 2 minus 1. And the change in time is 32 seconds minus 16. So the rate of the reaction is still 0.0625. Now let's look at another reaction. We're just looking at this hypothetical reaction where, let's just say, a red sphere goes and turns into a blue sphere. Now, because it's a 1-to-1 mole ratio and there's only one red thing and there's only one blue thing, the number of molecules will always total 100. The rate of the reaction can be measured as the speed of loss of red molecules over time, or we can do it as the speed of gain of blue molecules over time. So let's say we're starting off with 100 red molecules, and as red gets converted into blue, we can see that the total change, or the total number of molecules, is going to be 100, so 84. If we have 84 red, that means that we lost 16 to become blue. Now in this last column we have the rate of the reaction, and they've done the rate of the reaction just like we did on the previous slide. They've just done the work for us. But looking at this can be a little bit daunting, looking at all this data all at once. So chemists like to graph that data to better understand what's going on. So again, we're looking at that same reaction. We're starting off with 100 molecules of red spheres, and as time goes on, we see this decrease in the concentration of the red. So notice how we have this number of red molecules is decreasing over time. But the blue, because that's our product, this is going to be an increase in the number of blue molecules over time. So on the y-axis we have the number of molecules, on the x-axis we have the time. So we're looking at the concentration versus time. Now in this next graph, we've still got time on the x-axis, but on the y-axis we have the rate of the reaction. And notice that the rate of the reaction is slowing down. So as the reaction goes on, as time progresses, the reaction gets slower and slower. So it first starts off very fast, and then it starts to get slower and slower as time goes on. Now let's look at how stoichiometry can affect the reaction rates. In most reactions, the coefficients of the balanced equation are not all the same. So notice how in this reaction where hydrogen and iodine combine to make HI, it's a 1 to 2 mole ratio. Now for these reactions where you don't have the same coefficients in front in the balanced reaction, the change in the number of molecules of one substance is multiple of the change in number of molecules of another. So if we're looking at the above reaction, for every 1 mole of hydrogen used, we'll need 1 mole of I2. And so once you combine 1 mole of I2 and 1 mole of H2, you'll make 2 moles of HI. Therefore, the rate of change will be different, because for every 1 I2 molecule that you lose, you'll be producing 2 HI. So the change in the HI concentration should be twice as fast as the loss of the I2. Now, in order to be consistent, the change of the concentration of each substance is multiplied by 1 over that coefficient. So for HI, we would multiply that rate that we're determining by 1 over 2. So we take into account the difference in the stoichiometric amounts. Okay, so if we're calculating the rate for this reaction, so remember for H2, it'd be the change in concentration of the H2 over the change in time. And this is a reactant, so we need to put the negative out in front. Very similar for the I2. It's the change in I2 concentration over the change in time multiplied by a -1 because it's a reactant. And because there's a 2 out in front of the HI, the change in the HI concentration over the change in time is multiplied by 1 over 2. And we don't have to multiply by negative because this is a product, so it's just 1/2 times the change in HI over the change in time. Let's look at our first example problem. We have a reaction where we've got the decomposition of hydrogen peroxide combining with 3 equivalents of I- and 2 equivalents of protons, and this will make triiodide minus and 2 equivalents of water. And there's 2 things that they want us to do. They want the average rate in the first 10 seconds. And then they want us to determine the change in H+ concentration for this time interval. So let's look at doing the average rate in the first 10 seconds. So they've given us that the I- concentration changes from 1 molar to 0.868 molar. So since they've given me that information, I'm going to look at the rate of the reaction based on that I-. So I set up my general equation for my rate for my I-. So this is a reactant, so I need the -1 in front. There's a 3 coefficient in the balanced chemical equation, so I need to put a 1 over 3 coefficient. And we're looking at the change in the I- concentration over the change in time. So the change in concentration, the final concentration was 0.868 minus the initial, which was 1. This is what the concentration started out at. And our change in time, this was the first 10 seconds, so 10 minus 0, so the 10-second interval. Thus, the rate of the reaction is 4.4 times 10 to the -3 molar per second. So this is the average rate in the first 10 seconds. Now they want us to calculate the change in the proton concentration for this time interval. So they're looking for the delta H over delta T. So if we set up our rate reaction, so rate equals, let's see, because we're looking for the H+ concentration. So the H+ is a reactant, so we need the negative out in front. There's a 2 coefficient in front, so we need 1 over 2 times the change in H+ concentration over the change in time. So I calculated the rate above, and that was 4.4 times 10 to the -3. So I can substitute that in for my rate of the reaction. And I'm just going to solve this equation for the delta H over delta T. So I'm just going to multiply both sides by -2 to get this to cancel out. So the delta H over delta T equals -2 times the rate. So we found the rate above here, and I can just plug that in there. So the delta H over delta T is -2 times 4.4 times 10 to the minus third molars per second. The change in concentration of H plus over time is -8.8 times 10 to the minus third molar per second. So we're talking about rates of reaction, where there's two different types of rates that we can look at. First of all, there's the average rate and there's the instantaneous rate. The average rate is the change in concentration for any particular time period, and this is a linear approximation of a curve. And the larger the time interval, the more the average rate deviates from the instantaneous rate, and we'll show this on another slide. But this is kind of like how some cops actually will catch you speeding. I know that when I grew up in Arkansas, we'd have some cops sitting at one bridge on the interstate, and they would call in to their buddy at another bridge. They had already measured the distance, and they would time you to see how fast you were going. They'd calculate how fast you were going, because some people would see the cops, they'd throw on the brakes, and when they use the speed gun, they'd say, oh, they're going 70 on the interstate, which is the speed limit. But in reality, they were actually going much faster. They just had slowed down at that point. But if the cop takes the distance that they traveled and divided it by the time that they saw them going from one point to the other, they could get their average speed. So let's say you're going really fast in between the two bridges, and most of the time you're traveling about 90 or 95, but you see the cop of the next bridge and you slow down, and you're going 70 when you pass the cop, the second cop. But the cop knows that, hey, you've actually been speeding because it's 30 miles between the two bridges, and you pass 21 minutes later, and your average speed is 86. So even though he couldn't say with a speed gun that you were going faster, he knows by just your average speeds that you had to be going at least 86 at some point, and you were going above the speed limit, and so you got a ticket. That's kind of what the average rate is like. All you do is measure the change in time and the change in distance, or how far the reaction has progressed. But the instantaneous rate is the change in concentration at any one particular time. So this is the slope at one point of a curve. This is determined by taking the slope of a line that's tangent to the curve at that particular point. And if you've taken calculus, you know that this is the first derivation of that function. So the analogy for the instantaneous rate is when a cop uses a radar gun to get your speed right now. So it's instantaneous. Okay, so we're looking at this hypothetical reaction again. We're looking at red going to blue, and we're going to be calculating the average rates. In this first column, they're calculating the average rate in 5-second intervals. And in the second column, they're calculating it in 10-second intervals. And then the third, they're calculating it in 25-second intervals. So notice that you're getting different average rates depending upon the time periods that you're using to calculate those average rates. So the larger the time interval, the more error that you have. So just look at the difference between the average rate when you're looking at 10 seconds has passed in the 5-second column and the 10-second column. So in the 5-second column, the reaction is slowed down to 2.6 molecules per second. Whereas if you're looking at the average over 10 seconds, the average speed or the average change in concentration is 2.9, because you're looking at this entire 10 seconds. Whereas in the first one, you're only looking for 5 seconds. Now let's go down to the bottom, where at time 50, the average rate of the reaction based on the 5-second interval is 0.6. Well, in the last 10 seconds, they say the rate change, the average change is 0.7. And for the 25 seconds, the change is 1. So you've got a difference in the average rate depending upon the time period that you use. So that's one of the problems with using the average rates versus using the instantaneous rates. Now let's look at another reaction where we're converting the H2 to I and I2 to two equivalents of HI. So this is the same reaction that we had looked at previous. And they give us time on this first column, so time in seconds. We've got the concentration of the H2, and we've got the concentration of the HI. So we're just looking at the change of this H2, so one of our reactants, and the change in the HI, which is our product. And then the last two columns, they've already calculated the average rates for us. So the change in the hydrogen concentration over time and the change in the HI concentration over time. Now, just looking at this data, it can be kind of difficult to see what's going on. But we do kind of see this change in the rate of the reaction as the time progresses. It's getting slower and slower. So these numbers are getting smaller. But chemists like to graph. It's hard to see the relationship between the numbers by just looking at tables, and this is where graphing helps us understand what's going on. So in this graph, we're looking at the concentration of our reactants and our products on the y-axis versus time on the x-axis. So a couple of things to notice from this graph. Let's start off with our H2 concentration. Remember, H2 is one of our reactants, and we started off with a concentration of 1 molar. As time passes, the concentration is decreasing. So this has a negative slope to it, so you're losing some of the H2. But the HI concentration is increasing. But notice how much faster this concentration, or the slope of this line, the slope of this line for the HI is actually larger than the negative slope of the H2. And this is what we'd expect, because for every one H2 that we lose, we're producing 2 HI. So the production of HI should be twice as fast as losing the H2. Now remember, the average rate in a given time period is going to be the slope. So this is the change in the H plus concentration over the change in time. And again, remember, we wanted you to notice the negative slope of the line connecting the H2 points, and the slope of the HI points is positive, and it's twice that of the H2. So the average rate for the first 10 seconds is 0.0181 molar per second. And this is what we showed you in the chart on the previous slide. And we can calculate that rate again for these next 2 points, and the average rate for the first 40 seconds is 0.0150. And if we calculate the rate for these other points for the first 80 seconds, the average rate is 0.0108. So these are how we calculate the average rates. And notice how calculating the average rates, you have a deviation in the curves from the line. But the instantaneous rate, we need to draw the tangent line. The instantaneous rate is the slope of that tangent line. So let's say we're looking at time 50 here, and we're wanting to get the rate of the reaction at time 50. We draw a tangent line, and here we've drawn it for the HI. And if we calculate the slope of it, so the rise over the run, so the 0.56 over 40, we can get the instantaneous rate at that point. And we could do the same thing for the change in the H2 concentration. So at this time 50, we look at the change in the rise over the run. So the change in the concentration has gone down by 0.28 molar over 40 seconds. So this is how we would get the rate of the reaction at time 50 for the H2. So the H2, the instantaneous rate at 50 seconds is 0.0070. So remember, we took the rise over the run, so concentration went down by 0.28 molar, and that was a 40-second time period. And then using the HI concentration, so the red line here, and remember, because this is our product and we have 2 coefficients in the balanced chemical equation, we have to put the 1/2 out in front. So the rate of the reaction is 1/2 times the change in concentration, so that 56, over the change in time, so 40 seconds. So the rate of the reaction is 0.007 molar per second. So we get the same rate for looking at the reactant and the product. So this concludes our first lecture video for the kinetics chapter. We will begin looking at how we actually measure these reaction rates in the next video.